So the work that I will present today is a joint work with Antoine Chaillet, Andrei Miroshenko, and Fabian Wirth. And it's funded by the Bayes Institute. And I will talk about two main properties, which are forward completeness and bounded reachability sets that I will define for time delay systems. And my goal in this presentation is, so first to do a state of the art, but also to insist on the role of the state space. So throughout this presentation, I will introduce a new state space on which we believe that forward completeness and BRS, so bounded reachability sets, have really interesting properties. So in the middle of the presentation, I will introduce this new state space, and I will try to motivate it by some application to stability theory of time delay systems. And in particular, I will focus on global asymptotic stability and uniform global asymptotic stability of time delay systems. Okay, so let us start. So let us start by defining the properties of interest. So we first consider a general nonlinear dynamical system that takes this form. So x dot is f of x of t and u of t. So the state space is x. So typically, if you have an ODE, then the state space would be Rn. And the input space is U. So for example, you could consider measurable, essentially bounded inputs. But you could also consider other classes of inputs. So if we consider that this system is an ODE, then we would make some standing assumptions ensuring at least the local existence and uniqueness of solution. So we would ask that f is continuous and that f is locally Lipschitz continuous with respect to x and uniformly with respect to u. So this is only really to guarantee existence in uniqueness, at least on a small time interval of the solutions of the Cauchy problem that is associated. The first property of interest for this talk is forward completeness. So we will say that my system here is forward complete. So I will abridge this with FC. If for any initial condition x0 inside the state space and any input inside the input space, the Cauchy problem associated to this dynamical system and initialized at x0 admits a unique global solution. So a solution over the full non-negative time axis, so from 0 to plus infinity. And really, I want to insist in all my presentation on the fact that this property depends on both of the state space, x, and on the input space, u. And I will define later other possible state space and input space and other classes of systems. And then after forward completeness, I want to define the notion of bounded reachability sets that have already been seen in previous seminars of the same series on ISS. So bounded reachability set is also called robust forward completeness, so RFC. But in the presentation, I will always call this bounded reachability set. So we say that the system has the bounded reachability set property if it is forward complete, so it's a first requirement. And if, when we look at a bounded time interval, so t between 0 and r, at a bounded set of initial condition, so x0 in norm x is less than r, and at a bounded set of inputs inside the input space u, then the reachable set over this time interval and for these initial conditions and inputs is bounded, no matter how large is the ball. Okay, so for all r, we ask this set to be bounded. And a natural question is, why do we bother about BRS? Because forward completeness is really a natural condition, but why do we care about BRS? And the answer is that BRS is really the first bridge that we can make between the dynamical system theory that is interested into well-posedness of systems and stability and control theory. So that cares about the stability properties and about establishing bounds of solutions. So for example, BRS is used in the usual converse Lyapunov theorems that we have for ordinary differential equations. So if you start with an ODE that is globally asymptotically stable, and you want to prove that you have the existence of a smooth Lyapunov function, then we really need to use the BRS property to construct this Lyapunov function. It is also used for characterization of input to state stability, so ISS. as it has been shown by Fabian Wirs in the previous talk of the seminar series. And also for other stability properties, like the uniform global asymptotic stability property for time delay systems that was investigated in the paper by Karafilis, Pepe, Chaillet, and Wang last year. Okay, so the main question in dynamical system and control theory is it true or not that forward completeness imply BRS? So of course, BRS implies forward completeness because it is included in its definition, but does forward completeness imply BRS? So it is known since the seminal paper of Lin, Sontag, and Wang on converse-Lyapunov theorem that for ordinary differential equations, when we consider the input space as the space of measurable, essentially bounded locally inputs, then forward completeness does imply BRS. And that's why for people working with ODEs, sometimes we actually forget about the BRS condition that was used for smooth converse Lyapunov function theorem because it is granted for free inside the forward completeness requirements. But unfortunately, for a general infinite dimensional system, it is not the case anymore. Forward completeness does not imply BRS in general. It has been shown by Andrei Miroshenko and Fabian Wirs. And the counterexample that they build is simply an ensemble of infinite number, an infinite number of ODEs. And so the question remained for some time open for time delay system. So what happens for time delay system? Do we have that forward completeness imply BRS or not? And this is one of the questions that we want to review in this talk. So first, I will introduce these notations to define what is a time delay system. So a time delay system is dynamical systems that have the following form. So we define x dot of t as a function of xt, where xt is the history function that stores all the previous value of x of t over the time interval minus theta to 0. So minus theta is the maximal time delay on which the function actually depends. And then we have also dependence in an input u that lies inside an input space. So the history function here, for example, is in blue at the time t. So here you have x of t. So x of t is x index t at 0. And the state space, therefore, is typically an infinite dimensional space. And in the usual time delay system, what we choose is a state space of continuous functions over minus theta to 0. And therefore, an important point is that the initial condition is also continuous because it lies within this state space. So if you want to start your dynamical system at t equals 0 here, what you need is not only the value of x at 0, but also all the past history x0 over minus theta 3 up to 0. And here minus theta 3 would be my maximal delay. And in this presentation, I will restrict to the case of time delay systems that depends only of a finite number of delays. So I ask that my function f does not depend on the full history function, but only on x of t minus theta 1 up to x of t minus theta p, where p is a finite number of delays. And I assume that my delays are ordered. So theta 1 is the smallest delay, and theta p is the largest delay. Okay. So for this class of time delay systems, so with a finite number of delays, the standing assumptions to ensure at least the local existence of solution is that f is continuous with respect to all the variables, and f is also locally Lipschitz continuous with respect to each of the variables that depends on the state. So x of t minus theta 1, up to x of t minus theta p. And this must be uniform with respect to u, okay? And we will always work in this presentation under these standing assumptions for time delay system with finite number of delays. So for this class of system, do we have that forward completeness imply BRS? And the main question that we want to address here is, how does it depend on X? So how does it depend on the state space, which is the space also of the initial condition? So it's the space in which lies the history function. So for many years, it remained an open question, but in 2 years, we had 2 different answers. The first one was, the idea was to restrict the state space to the space of Hölder function. So X would be C0A, where A is some parameter between 0 and 1. So this is a Hölder space. And I recall that some function phi would be inside the Hölder space if it is continuous, and the supremum of phi s minus phi tau over s minus tau to the power a is less than infinity. So typically, if you take a equal to 1, you recover the definition of Lipschitz continuity, okay? And in their paper, Karafilis, Pepe, Chaillet, and Wang proved 2 years ago that for time delay system over the state space of Hölder functions, and in the case where you have no inputs, then forward completeness does imply BRS. So you recover the usual result that holds for ODE. So it remains until now an open question whether or not this result is still true with inputs. And to work with that, the idea would be to use the compactness arguments that comes from the fact that X is an Hölder space. So basically that comes from Arcela-Ascoli theorem, and then to try to merge it maybe with the usual ODE theory. But this remains until now an open question. But here, to obtain this result that forward completeness implies BRS, we need to restrict the state space to this, while the usual state space would be the state space of continuous function. And in a very recent work, Mansilla, Aguilar, and Emovich proved that for time delay system over continuous state space, and for inputs that are in L infinity lock, so the space of measurable and locally essentially bounded functions, forward completeness, unfortunately, does not imply bounded reachability sets. So this has deep implications. For example, if you have listened to the talk of Fabian Wiers, you know that BRS is really an important assumption to derive ISS superposition theorem or other things like that. And the thing is that therefore we need really to assume BRS, and it's not granted for free by forward completeness, okay? So I will not go into the proof, of course, because, well, first you can look at the paper of Mansilla, Aguilar, and Emovich, but I also advise you to look at the great YouTube video of Emovich explaining this work in the ISS seminar series. But I just want to recall one of the key arguments of the proof, and that we will use in our work. It is the fact that to an OD with a finite number of delays, to a time delay system with a finite number of delays, we can associate an OD. So if we consider this time delay system, we can then consider the ODE that has as inputs V1 up to VP and U. And the idea is simply each time that you have a delay, you replace this by some new input, okay? So the time delay system has a state space X and an input space U, and the ODE has a state space that is Rn, because it is an ODE, as an input space that is V times U, where V is the input space in which lie V1 up to VP. And so there will be a link between the state space X, because it's X of T minus T1 and etc. up to X of T minus theta P. All this regularity depends on the state space. And therefore, if you try to replace it by some inputs, then it will have an impact on the choice of the input space, okay? So the key proposition is that you have a link between the solutions of the time delay system and the solution of the ordinary differential equations that is associated to this time delay system. So the easiest way is to start with the time delay system. So of course, if xt is the solution of the time delay system, then x of t is a solution of the ordinary differential equation when you choose as input vk of t being xt of minus theta k. So xt of minus theta k is nothing else than x of t minus theta k. And you see that since the input coincide, well, the solution also coincide. But the interesting and important fact is that you can also go the other way around under the condition that you do this only on a small time interval. So the idea is that if x of t is a solution of the ODE for some inputs V1 up to VP and U, then you can try to construct an initial condition, so x0, such that on a small time interval, well, x0 of t minus theta 1 up to x0 of t minus theta p will coincide with the input V1 up to VP. So this is what I try to represent on this graph. So here in blue, you have the future values of the inputs that you want to apply to x of t, and you try to make it coincide with the initial condition x0. And on the things that are not defined, well, you can put anything because it is not used inside the dynamics, okay? But the main important point is that you cannot do this indefinitely, because as soon that you have a crossing between the V2, for example, and V3, then you cannot do that anymore, because X0 would be defined differently, so 2 times and differently. So here you see that if you want to define X0 at minus theta 2, it must coincide with V3 at 0. But if you wait a time that is too long, then it should also coincide with V2 at time T2 plus theta 3. And this would be a contradiction if V2 and theta 3 does not, and V3 does not coincide, okay? So for this reason, you can also only do this up a time interval delta, that is the minimum distance between 2 different delays, including 0 as a potential delay. Okay. So this is really the key ingredient in proving that forward completeness does not imply BRS for the state space of continuous functions. And I try to summarize the strategy with the following graph. So the idea of the proof is you start here on the bottom left, okay? And you consider a time delay system over the state space x0. So what I call x0 here is the state space of continuous function over minus theta p0 into Rn. And you assume that this system is forward complete. Then from the work of Mansilla, Aguilar, and Emovich, we know that the corresponding ODE, so the ODE that is associated to the time delay system, is also forward complete for continuous inputs. And actually, it's equivalent properties. Okay. Similarly, the same system has the BRS property if the corresponding associated ODE is forward complete for inputs that are in what I call V infinity, which is a space of inputs that are locally essentially bounded. But it is known that there are ODEs that are forward complete for continuous inputs, but not forward complete for L infinity inputs. And this is this work. So this arrow here, we know that it is wrong. Okay, so therefore, following this path here, so the red lines, we see that forward completeness of the time delay system over the state space of continuous function cannot imply the BRS property. Here on the right, I represent relations with the property of the ODEs. So we know that for ODEs, forward completeness over L infinity inputs is equivalent to the BRS property. So this is the finite dimensional case. It comes from the work on smooth converse Lyapunov function theorems. And obviously, all the arrows that are in black here are obvious arrows, which means that if you do not change the system and the state space, BRS always implies forward completeness. And also, if you restrict the state space and you keep the same property, then you also have an implication. Okay. So this is for the state of the art after the recent work. And in the work that I want to present, the intuition was, okay, this implication that does not work, it really does not work because we have a relation between here the ODE with continuous inputs. And so maybe what we should do if we really want to guarantee that forward completeness imply BRS over a time delay system is to consider a state space for the time delay system that would be L infinity over minus theta p0. So this is the intuition of our work. And the first question is this kind of time delay system well posed when we consider this kind of state space? And unfortunately, things are not that easy. And this is the new state space that I want to introduce in the next slides. So to show you why it is not that easy, I will recall first the notion of solution for the time delay system independently of the state space. So here the state space is just X. So given an initial condition X0, so an history function from minus theta 0 to 0, inside the state space X, we say that we have a solution, so a map from T to X index T inside the state space over some time interval 0 to capital T. So capital T is the time of existence of the solution. If this function is absolutely continuous and satisfies this integral equation over the full time interval. So X of T must be X0 at 0, which is nothing else than the initial condition of your system, plus some integral from 0 to T of X X index tau actually, and U of tau. The problem is that when you formulate solutions like this, and then you try to prove existence and uniqueness of local solution, then you formulate this problem as a fixed point, and then you apply shorter fixed point theorem. The problem is that you really need here, in this part, to define the value x0 at 0. And it is not possible to do that if your function is only in L infinity. So I try to illustrate this here in this very easy example. So if you say that this is your L infinity function that is x0, and you say you initialize your time delay system here, then you have to also specify at which point you really start at 0. But this is not specified with the usual L infinity state space. So it means that your time delay system cannot be well defined with this state space. So we need to add something. And actually what we need to add is the specific value of the function at t equals 0. And this is the new state space, which is x infinity that I want to define now. So I say that x infinity is a space of classes of measurable, essentially bounded function from minus theta p0 to Rn, where we identify two functions when they are equal almost everywhere. So if I stop my sentence here, it's just L infinity. But if they also coincide at 0, so I add one extra condition. So it makes that this state space is actually isometrically isomorphic to L infinity times Rn, because it's the data of an L infinity function plus some points, that is the value at 0. And we can define a norm on this state space, which is the maximum between the L infinity norm and the usual norm in Rn of x of t, which is xt at 0. And in this new state space, then we can prove, and it is known from Delfour and Mitter in 72, that the Cauchy problem is well posed, at least locally. So for each initial condition in x infinity and each input in L infinity loc, the Cauchy problem emits a unique maximal solution remaining in this state space. But this is feasible only for time delay system with a finite number of delays. And this is one of the reasons for which my presentation, I have a finite number of delays. There are two things on which we need to be careful with this state space. So first, we need to have a finite number of delays. But the second thing on which we need to be careful is that the flow may not be continuous. And this may be a problem in some propositions. So we need to be really careful about that. The fact is, for example, if you consider the initial condition that we had, and you just add the dynamics x dot equal to 0. So what happens is that the history function here, after a small time t, is represented by the red function. And if you look at the difference in x infinity norm between x of t and x0, then this will always be 1. I mean, it will always be positive, because it's the difference here between this function and this function can never be 0 in the L infinity norm. So even if t is very small. So really this flow, it cannot be continuous. However, if we wait for a sufficiently long time, which is the maximal time delay, so after t greater than theta p, then we recover the continuity. And the reason for that is that the initial condition is somehow forgotten after a time interval of 0 theta p, because then all the initial condition has become absolutely continuous, because we know that the solution t maps to x of t is absolutely continuous from t equal to 0. And so it's like after your theta p, you add a new initial condition. This new initial condition is absolutely continuous, and in particular continuous. And therefore the flow is continuous, okay? But it's not true to say that for t small, this map is continuous. Okay. So now do we have that forward completeness implies BRS for time delay system over this new state space x infinity? Because this is our initial hope, initial intuition. So here I just recall exactly the same graphs than before. So this is the state of the art for time delay system over x0. So x0 is a state space of continuous functions. And the equivalences are equivalences with the associated ODE. So the ODE that is associated to the time delay system. So with the same map F. So at this point in the presentation, I will ask you to twist your eyes and to work a bit on your representation of 3 dimensions, because this is exactly the same graph than before. So here you recover the same 2 equivalences given by Mansilla, Aguilar, and Emovich. So it's really exactly the same graph. And the reason why I twist it like that is because I want to introduce two other properties that are the fact that the time delay system is forward complete or BRS over the state infinity times Rn. Okay. And the question is, can we somehow complete this square here? Can we find all the implications that are true and all the implications that are false within this square? So we start with the obvious arrows. So of course, if you do not change the state space, BRS always implies forward completeness. And also, if you have some property in X infinity, then it is also satisfied in X0 because X0 is a smaller state space than X infinity. And then what happens is that what is missing to complete all the cube in terms of equivalences are these three blue arrows. And this is our work. This is the proposition that we prove and that I will present to you now. And with this, you see that if you start on the bottom left, so with the time delay system over X infinity that is forward complete, then with this first blue arrow, you can go to the fact that the associated ordinary differential equation is forward complete for L infinity inputs. And we know that this is equivalent to the BRS property on the ODE. And then with this new blue arrow, we prove that the time delay system is bounded as bounded reachable set over the state space X infinity. So we do have that forward completeness and BRS, again, are equivalent properties over this new state space. If I summarize this cube of implications, I have the following result. So actually, all the properties of the cube, these first 6 properties, sorry, are all equivalent assertions. So if I try to summarize, all the BRS conditions are equivalent. So having BRS in some state space does not depend on the state space for the time delay system. And it is also equivalent to the ODE being BRS. And it's, again, independent of the input space of the ODE. And these properties are also equivalent to forward completeness when we consider for the time delay system the state space X infinity, or when we are with the ODE, when we consider the input space V infinity. So if I summarize, all the BRS properties are equivalent. All the L infinity properties somehow are equivalent. And then there are 2 weaker conditions that are implied by the above, but that do not imply the above. So it's time delay system being forward complete for continuous inputs, for continuous state space, so X0, and the ODE being forward complete for continuous inputs. And now we have all the map for all this graph is summarized by these implications. Okay. So I will briefly sketch the proof of the main proposition. So essentially of the fact that over the X infinity and for U equal L infinity log, we do have that forward completeness imply BRS. So the first step is to say that if the time delay system is forward complete over X infinity, then the ODE is also forward complete for inputs that are L infinity. Then we show, so we know that this property is equivalent to BRS for the ODE. And then we show that for the associated time delay system, we have the BRS property over X infinity. And the 2 proofs are really similar, and they exploit the relationships that we have between the solution of the time delay system and the solutions of the ODE. So the first one is a proof by contradiction. So if you assume that your system of your ODE is not forward complete, okay, then it explodes in some finite time, t less than infinity. But then if you fix this finite time and you find, you fix delta small enough such that over t minus delta t, the solutions of the ODE are also solutions of the time delay systems for some well-chosen initial condition. So this is the proposition that we have seen before, that you choose the initial condition in terms of the input of the ODE. And if you do that, you have the same trajectories for the time delay system and the ODE. But then since your time delay system is supposed to be forward complete, you get the contradiction. And this proves the proposition. The second proposition is again a proof by contradiction. So we assume that, so we want to prove that if the ODE is BRS for L infinity input, then the time delay system is BRS for the state space X infinity. So I recall that BRS means that for any positive time and any positive constant R, the supremum of the trajectory for all time being between 0 and t and all initial conditions bounded by R and all inputs bounded by R is less than infinity. But due to the semi-flow property, we can replace this for all by there exist. So the reason for that is if there exists some time such that this is bounded for all positive R, then you can apply this property over the time interval t. So your solutions remain bounded at some time interval. But then you can again apply the proposition starting from this new bounded set. And then again, over the time interval of length t, you remain bounded. And therefore, doing by induction like that, you prove that you can prove that you have the proposition with the fall here. Okay. So knowing this, you just now fix some t that is less than the smallest delay, so θ1. And then over this time interval, the solution of the time delay system, they coincide with the solution of the ODE. But the main point is that the input, since it is chosen with respect to the initial condition of the state space, and since t is less than the smallest delay, the input really coincide with x0. And therefore it is bounded because you have chosen here a bounded set of initial conditions. So you get the BRS, you get a contradiction with the BRS for the ODE. Okay. So the proofs are not really difficult, but they really follow the idea of exploiting the fact that solution of the TDS and ODE coincide if you choose well either the initial condition of the time delay system, or conversely, if you choose well the inputs of the ODE. So now that we have seen all these properties, so that forward completeness does imply BRS over the state space L infinity times Rn, natural question is, what can we do with this result? So can we try to relax some stability theorems that are known, and mainly to try to remove the BRS assumption in theorems that are already known? So my application is to the case of characterization of global asymptotic stability and uniform global asymptotic stability for time delay system. So since I care about global asymptotic stability properties, I will forget about the input here. So I consider a time delay system that has no input. So the input space U is just void, okay? So I will recall the definition of global asymptotic stability and uniform global asymptotic stability first. So we say that the system is locally stable if for any positive epsilon, there exists some delta such that the supremum of the trajectory over all the initial conditions that are less than delta is actually less than epsilon. So this is the usual definition of Lyapunov stability. Then we have the global attractivity property. So we ask that for any initial condition in the state space, the norm of xt x0 tends towards 0 as time goes to infinity. And global asymptotic stability is just the combination of local stability and global attractivity. And uniform global asymptotic stability looks like a stronger property. It asks the existence of a function beta that is a function of class KL that I will define, such that the norm of xt at x0, so depending on x0, sorry, is less than beta of the norm of x0 and t. So I recall that I say that beta is of class KL. It means that in the first variable, it is a function that is 0 at 0 and that is increasing. So beta here is representing in green when the dependence into the first parameter is represented in green. And also with respect to the second parameter, it is non-increasing and tends towards 0 at infinity. So here we have the dependence of beta in red in the second parameter, okay? So it is well known that for ordinary differential equations, we do have the equivalence between gas and U-gas, but it is not the case anymore in general for infinite dimensional system, and it is not even granted for time delay system. and I will recall what is the state of the art for time delay system. So first I will start again with Hölder spaces. So we try to restrict our state space to get stronger results. So in their paper, Karafilis, Pepe, Chaillet, and Wang proved that since we have that forward completeness implies BRS in this state space, then we do have that gas implies UGAS. And this is really because we have BRS. But if we consider a state space of continuous function, then in general, what we have is that BRS and gas is equivalent to UGAS. So since we know that forward completeness does not imply BRS, we can also show, I mean, Mansilla, Aguilar, and Emovich proved that gas does not imply UGAS. And this is for continuous state space. And so now the natural question is what happens for X infinity? Because we have learned that for X infinity, forward completeness implies BRS. So naturally, we would expect that again, gas implies UGAS. So if we try to complete our equivalent, our implications, so obviously we have x0. So x0 is continuous function imply x0 gas, and the converse is not true. Then we add our two new properties, which are UGAS and gas, with respect to the state space X infinity. So X infinity, again, it's L infinity times Rn. So again, all implications that are here in black and with no reference are obvious, because if you keep the same state space, UGAS implies gas. And if you choose a weaker state space, then you keep the same properties. Okay. And we try to complete these arrows. And what happens and what we proved is that we can add these two blue arrows. And therefore, if you start with X infinity global asymptotic stability, then you can prove that you have that the same time delay system with the state space of continuous function is uniformly globally asymptotically stable. And then this in turn implies the X infinity UGAS. Okay. So if I summarize, again, all the following assertions are equivalent. So time delay system is globally asymptotically stable with a state space of X infinity, or the time delay system is uniformly globally asymptotically stable with either the state space of X infinity or the state space X0, which is the state space of continuous function. And these properties imply and are not implied by the X0 gas, so global asymptotic stability of the time delay system for the continuous functions state space. So we briefly sketch the proof of these two main implications. So the first one is quite clear. So for time delay system with no inputs, we have that X infinity UGAS imply X0 UGAS. So what is the proof of that? We start with X infinity gas. Then obviously it implies X0 gas because you just reduce the state space, okay? But it also implies X infinity forward completeness, because when we say that we are gas, we have in mind that we are also forward complete, okay? By the previous results that we have shown, so which is the main result of our work, we know that X infinity forward complete does imply X0 BRS. Actually, it implies X infinity BRS, which is in turn equivalent to X0 BRS. But by the result of Karafilis and co-authors, X0 gas and X0 BRS imply X0 UGAS. So you get the X0 gas from the assumption here, the X0 BRS from our previous work, and you get that the system is X0 UGAS. Then what we want to prove is that X0 UGAS does imply X infinity UGAS. So we start with X0 UGAS. It implies that the system is X0 BRS, so this is clear. And by our characterization of forward completeness and BRS, we know that X0 BRS does imply X infinity BRS, because all the BRS property for the time delay system are equivalent now. And then the idea of the proof is the following. So it's a bit more intricate, but not very difficult. So on the first time interval, so until the maximum time delay, which is theta p, we use the bounded reachable set property over X infinity to control the size of the X infinity solutions. So we know that over this time interval, which is finite, the solutions remain in a bounded set, okay? And then over theta p to plus infinity, we know that the x infinity solution actually coincide with x0 solutions. Why? It's because since the solution t maps to x of t is absolutely continuous from t equal to 0, the solution starting at theta p is just a solution of the time delay system with initial condition that is the solution over 0 theta p, which is continuous. And therefore, these two kinds of solutions coincide after theta p. And therefore, we can use the property of x0u gas to control with a beta function of class KL the size of the solutions. So on the first time, and then we combine these two properties. So on the first bounded time interval, and then over theta p to plus infinity, to construct a common beta function over these two time intervals. And we have the result that the system is x infinity UGAS. Okay. So I arrived to the conclusion. So in the end, what I want to underline is that with this result, what we know is that for time delay system, mainly the state space L infinity times Rn and the input space of locally essentially bounded measurable functions guarantees that forward completeness does imply BRS. It may sound a bit surprising because now if you combine all the results that we have in the literature, there is forward completeness implies BRS for all the spaces and in X infinity. So for the smaller and the larger state space. But forward completeness does not imply BRS for the state space of continuous functions, which is in the middle. So it may sound a bit surprising. Actually, it's not that surprising because it's really due to the fact that in ODE theory, you do not have that forward completeness imply BRS if you restrict to the space of continuous inputs. And that's really the main reason why you have this kind of intertwined properties. So we believe that our works really open the door to trying to relax many characterization of stability properties. So in particular for ISS superposition theorem, in infinite dimension, even for time delay system, what we have most of the time are theorems that sound like PRS plus some properties, some stability properties, are equivalent to input to state stabilities. And the fact is that if forward completeness implies BRS, then we can remove the BRS assumption, and therefore we can have a stronger result. The question is this really natural? Because it would require to recast all the existing results of time delay system over this new state space. And with this, we get nice stability properties because we have forward completeness imply BRS. It is a larger state space, so in some sense, it's maybe better than continuous function. But on the other hand, we lose some properties that are useful and sometimes interesting, and mainly the continuity of the flow. So for me, it's really an open question. Is this state space somehow natural? And does it worth it to recast the existing result in this state space? And another thing on which we should work is what can we say for time delay system with distributed delays over the state space? And there are two main problems when we try to extend the theory to distributed delays. The first problem is really the pure well-posedness theory. So the well-posedness theory for time delay system is well known by the work of Delfaux and Meter in 72 over state space that look like LP times Rn when P is less than infinity. But when P is equal to infinity, lots of things fail and you lose your Cauchy-Lipschitz-like theorem, except in the case where you have a finite number of delays. And therefore, it's not clear at all what you can do with distributed delays and P equal to plus infinity. But still, we could assume that we have existence and uniqueness of local solution for a given system and wonder if the forward completeness implies the BRS property. And here we face the other issue, that is the relation with the ordinary differential equations. Because this relation is really nice to establish counterexamples, to build proof by contradictions, for example, but it completely fails when we work with distributed delays because, of course, we do not have the correspondence anymore. We cannot put a finite dimensional input that would correspond to the past value of the state. We cannot construct initial condition of the state space that would coincide with the given input that would be finite dimensional. So we do not know yet how to try to do that. Okay, so this is the end of this talk. Thank you very much for your attention, and I'm open to questions.